Hello and welcome to this video. We have here the evaporation at a liquid surface which we consider, and by this I will also introduce the Stefan flow and its importance for mass transfer. Let's have a look into what's happening. We have here a video that we took in our lab. We did put a glass of water and just let it sit there and took a camera an image every single day, and you see the video from all of these images. We would like to understand the specifics of this evaporation process as a learning goal, and as such also you will get knowledge about the Stefan flow. And what we have here, we have ambient air, which we call component B, and water, which we call component A, regardless whether it's water vapor in the air or in the liquid. And we see we took a photo every single day. This is a quite slow process. And the question that is coming up from here is, how large is the evaporating mass flow or the mass flow rate? And I can tell you this was running up to day 40. Now let's move on here. We have here a sketch of the water glass with the water here. There's a glass, there's outside air, which I gave here a gas flow. It's not needed that we have a gas flow, however we need a boundary condition over there. There you see a coordinates that starts at the surface. Now let's have a closer look. What is the problem? We can define at the liquid surface we have a mass fraction of A, S indicates the surface, and that typically is determined by a vapor pressure correlation because it's considered to be saturated, as I have mentioned here. Now far away in the ambient air, I assume that there is no water vapor present, and psi B equals then 1. We also have a surface fraction of B, which is psi Bs, which is non-zero. So this means I have a driving potential for the red marked psi B and a driving potential for the blue marked psi A. And these differences are both non-zero, so I get the establishment of diffusional flows. The specifics of this problem is here related to this surface. And here you see these diffusional flows. I will elaborate in a second how I get to those. And this impermeable surface for B but permeable for A we call semi-permeable, and there's a little video that illustrates that. So we see the blue molecules that move into the gas phase. However, the gas phase originally just made out of component B cannot cross the liquid surface, and this has certain consequences, and these consequences I'd like to discuss here. I have here a sketch with X over Xi plotted, and I will now put in the values that we know already. So let me start here with the blue mark Xi A. We know here we have the saturation condition at the surface. Here I gave it the value 0. So typically I have a curve something like that. There's an artifact. Let me get rid of this one and redo it. So somehow a line like this. It is curved. I will show the correct profile at the end here. For now, let's just assume we have such a profile, and this drives, we see the gradient, and then it's very clear we have a diffusional flow, area specific because we have the same area, and that's diffusional flow of A. And we also know that we have psi A plus psi B to equal 1 in this case, and this means I can immediately draw also the profile for the air. So I have psi B here, psi B infinity, and some non-zero value at the surface, and this means I get something like that with the establishment of a diffusional flow of the ambient air component B towards the surface. Well, we said, let me take another color here, we said this surface is impermeable to the air, and this means, well, I do not have a mechanism that accumulates air there. There's no black hole to eat the air away, so the air has to somehow get back. And this drives the establishment of a convective flow that's shown here. And this convective flow, let me use then another color, carries everything here out. This means it carries B away so that the mass flow rate by diffusion is compensated by convection, and it augments the diffusional flow of A because it helps to carry A away from the surface. So let's look at that in the next slide here. Because the surface is impermeable to B, we saw that this diffusional flow of B must be balanced by the convective flow that I'm showing here. And this means the mass flow rate by diffusion is minus the mass flow rate by convection and vice versa. And the consequence for A is that the diffusional flow rate of A gets enhanced by this convection. And now let's do some math. And we see here some picture on the left hand side that I will explain here by my equations. The mass flow rate for A, as I did in the previous video, I can just formally separate that into, let me take another color here, into a diffusional and a convective part, and expressed by chi A dot 2 primes plus rho V times psi A. And I can write the same thing down for B. That's just a formal approach, no analysis so far. Now let's do the analysis. And the first one was, we said that these two equal each other with a negative sign, so I get a 0 for the mass flow rate of B. That's my equation 3. I make use of that and put it into my equation 2, so I get here the expressions rho V psi B equals minus JB dot 2 primes. And of course I can add up equation 1 and 2, that's what I'm doing here, to get this equation. And we understand that this here has a sum of 1, and I also showed in the lecture earlier that the sum of the diffusional fluxes with respect to the center of gravity velocity are 0. So I end up here with an equation that says m dot A, because I made use of this here as well, is rho V, and this is the total mass flow rate that is escaping from the liquid, so I don't need any indices, it's just m dot 2 primes. And this I can now put back into equation 1, make use of the other findings, and I end up with this equation 7, where m dot is m dot times psi A plus ja dot 2 primes. And this I will analyze a bit further here. It's just rewritten. And the psi, let me go back one here. Here I did not specify the psi, but I know only the value at the surface if I use the vapor pressure correlation. In between I don't know the values of psi, so that's why I'm looking at the surface value here. And that's why I have the S in this equation. Now, the diffusional flux is not, it's just a steady state condition, so it's the same in whatever x coordinate, so I'm not taking the S here any further, but for psi S I take it further. And let me now have a look at, let me take now the laser pointer, that's easier. Now we can resolve here for m dot, and m dot is 1 over 1 minus psi AS times JA. And this is the so-called Stefan factor, and if the vapor pressure is high, this value is larger, so this thing becomes smaller and the overall factor is growing, and it's always larger than 1. So this Stefan factor is enhancing the diffusional flow. And the mass transfer coefficient I can use now to describe chi A And this is similar to the heat transfer equation that we used so far to deliver now an equation to calculate m dot A. So it's the mass transfer coefficient times the driving potential divided by the Stefan factor. Or Stefan factor is 1 over that, so it's just Stefan factor times G times the driving potential. Now let's move forward here and have a look at if we can determine, this is the dimensional analysis, and if we go to non-dimensional notation, we'll make use of the definition for Sherwood number, resolve that for G, so I get Sherwood times rho d over L, and now I massage this a little bit, so I add an eta here and an eta there, and try to get to a Reynolds number and a Schmidt number, and then I keep rho v infinity as a leftover. So the entire non-dimensional formulation is m dot 2 primes divided by rho v infinity, and then you see here a grouping of non-dimensional numbers, Sherwood divided by Schmidt and Reynolds, times the driving potential times the Stefan factor. And that's what I wanted to show you, and I forgot to explain in the previous, I said that this is 0, and we see here that there is a small contribution by convection, which makes the total mass flow rate larger than just the diffusional one. And this brings me at the end to show you the correct profiles. The correct profiles are curved, and this curvature comes by the velocity that is establishing, and this means that we have a curvature like that and that, but this is not part of this course. That will be done in a master course. However, this master course at this point in time is available in German only. That's WSU2. And this brings me to the final questions. The first question is, what causes this additional convection? What does it compensate for, and which parameter influences the amplification of the mass flow rate by convection in a significant way? So think about that. If you can answer the questions, fine. If not, go and recheck the section of the video again. Thank you for listening.